While you were watching Blue's Clues in the kids' room at the age of 7, I was solving geopolitical issues in the peaceful Balkans. How about diplomacy? How about I bomb you into oblivion and then we talk? You gotta find out real quick why we don't have a functional social system. Anyway, for the past month I've been reading the source code of the first Command and Conquer, Tiberian Dawn from 1995. And brother, we gotta talk. For the most part, the codebase is very good, no doubt. I mean, you had legendary level developers on the team. But I've seen some things that would get you fired in 2026. Like, for example, this Exodia header file that includes everything and is included by everything, or the coupling is so hard it makes portability more difficult than life in Bosnia. I mean, just seeing this header file made me feel violated. This should be illegal. But there's a huge lesson in all of this, I promise. Especially for the people who keep asking themselves, am I good enough to start? Should I do this or that? And end up stuck in this paralysis, doing nothing. Because overthinking is the only thinking they have. So in this video, I'm gonna break down the source code of Command & Conquer Tiberian Dawn. Here's the roadmap of the video. First, we're gonna talk about the architecture of the game, black box and white box. Then we're gonna unroll the main loop. Then I'm gonna do 6 technical breakdowns, starting with the less difficult ones and then increasing the complexity with each chapter. We're gonna cover the Vodcom compiler and thus 4GW runtime, the game data assets coupling to the engine, the header file Function.h, the event queue system single player and multiplayer, with lockstep netcode, the fog of war mechanics, and pathfinding. And then I'm gonna draw some conclusions. Now, since we don't have any documentation besides the comments in the code, analyzing the source code was quite a challenge. So if I got anything wrong or the original developers want to chime in, feel free to use the comment section. Joe Bostic and the rest of the team, if you're watching, you made my childhood so much better, and I mean it. I have to admit I didn't play it in 95 because in 95 we had war at home, but it was the first RTS game I've ever seen. This was around the year 2000 probably, and later on I played everything my computer could run, StarCraft, Warcraft, KKND, Age of Empires and so on, but Command & Conquer made me a fan of the genre for sure. Now, if you open the Git project, you'll see it doesn't provide any technical documentation on the software architecture. The source files aren't even grouped into folders or modules or whatever, which was very usual for that era. And I'm now gonna walk you through my thinking process when analyzing any undocumented legacy project. Mentally, we need to start at the top abstraction level. So let's draw a black box in the middle. Stuff goes in, stuff comes out. On the input side, we have keyboard and mouse from the player, and in the multiplayer we also have network packets coming in. Inside the box, the runtime gets those inputs, so the simulation, the world state advances. On the output side, we get visuals on the screen, audio output, and in multiplayer, the game also sends network packets back to other players. So that's the general idea. You press a key, beep boop, and things start happening on the screen. Okay, now let's start looking inside all of this. So after black box comes white box. But keep in mind, we're still operating on a high abstraction level. Before touching any code, we need a mental model. Just a rough picture of how the system probably works. Okay, so this is a game, and games usually split into 2 big chunks. In the middle you have the engine, and next to it you have game assets, data, content, resources. In Command & Conquer, the assets are stored in .mix files. Every project does this differently under the hood, but the pattern is always the same. The engine reads assets and turns them into something the runtime can use. Now we need inputs. One path is the player, keyboard and mouse, handled by an input subsystem. The other path is multiplayer network traffic, handled by a networking subsystem. Those 2 streams have to converge somewhere. Typically, they get translated into events and pushed into a single event queue. And that event queue becomes the engine's feed, so to speak. It's how the engine consumes everything the outside world is trying to tell it. With assets loaded and the events flowing in, the engine advances the simulation on each tick at a specific frequency. And after each tick, the engine pushes results into the output channels, rendering, audio, and during multiplayer, outgoing network packets to other players. Now, we're gonna take a look at the implementation for some of these modules. Okay, let's start with the game data, the .mix files. And let's open init.cpp. Now, before touching .mix files, init game first presizes core object heaps. For example, for units, buildings, bullets, and so on. In plain terms, it reserves the memory first and then moves into the asset loading. And now, if we scroll further down at some point, it starts loading the mix files. Okay, conquer.mix, transit.mix, general.mix, and so on. As you can see, they implemented this mix file class object to take care of that. So let's take a look what's inside of it. So mix file class opens the .mix file, reads header metadata like count and data size, allocates a subblock table, and loads that index into memory. This is basically archive indexing for fast lookups later. This is not gameplay logic, it's only the assets, the game data, okay? Okay, now let's continue with the input lanes. The main idea in Command and Conquer event handling is that we have two event lists, basically two buffers. The first one is outlist. This is where local player commands land first, already translated into events. So when you click something, your click gets transformed into an event, and that event is stored in outlist. Think of outlist like a mail-out box. From there, events get moved into the second list, the do list. Do list is more like a calendar. It doesn't just store what should happen, it also stores when it should happen, on which frame the event gets executed. In the code, the two lists look like this: outlist and do list. So basically, outlist is command just created, and do list is command ready to execute at the correct frame. Now, for the single player, it's easy. You're getting the key inputs, create events, and then push those events from the outlist queue to the do list queue. But when we play multiplayer, it gets a bit more complicated. Now, let's go through a multiplayer example. Imagine we have the player A client and player B client. Both clients get the local input and create an event. The event is then pushed into their own local do list and via the network to the other player's do list. So all the events for local input and network input end up in both do lists. And of course, we have network headers and stuff in here. This is just a very simplified diagram on what happens. The sender has to pack the events properly, and the receiver has to parse and interpret the packets properly and then push them into the do list, of course. Okay, then the inputs get processed. When the game state advances, the output gets sent out to the output channels, rendering, and audio. That was the white box. Now let's unroll the main loop. When talking about the main loop in Command and Conquer, we have to split it up into the main game, which handles the session level loop, and the main loop, which handles the per frame loop. If we open conquer.cpp, we can find the main game function. So that's the outer shell. Init once, then keep running sessions while select game says we should. And this is the inner heartbeat. Main game keeps calling main loop until main loop says we're done. Now let's take a look inside main loop. Inside main loop, we first configure the frame pacing. So before we do gameplay work, the loop decides how fast this frame should run. That keeps the rest of the frame on a predictable rhythm. Next is the input plus render pass. This is the part everyone expects to see in a game loop. Read input, process key actions, and draw the current state. Straight line, no magic. Then we do simulation and queue processing. This is the center of the frame, so word logic updates in logic.ai. Then the event queue system is managed by queue_AI. And after that, the frame advances and timing is closed out. So frame plus plus is the clock tick, and sync delay is the pacing guard so the loop doesn't outrun its own time policy. The main loop stops when main loop returns false game active, and the caller checks that return and breaks. Now, one quick context note before we move on. From a multiplayer perspective, Command and Conquer is lockstep driven. It's not a modern, tick-driven engine with a client and server architecture and authoritative game states. Lockstep means peers exchange commands and execute them on scheduled frames. And fast peers wait if they run ahead or miss commands. A server-fixed tick engine, like for example in Counter-Strike, runs the simulation with a strict frequency. I made like 100 videos on this. More like 5 videos, but you get my point. So that is the practical mental model. Outer loop runs the session, inner loop runs the frames. Each frame reads input, renders, runs simulation, pumps events, advances time, and checks whether the game should keep running. Okay, we have covered now the basics. Generally speaking, most interns, students, or younger colleagues I worked with have this misconception that you solve big problems by throwing some huge complicated math equation at them. But the reality is, you need to develop a feel for logic first. Ask the right questions before you try to hunt for the right solution. You have to know how to break a problem down properly, and then build these small mathematical and logical bridges to get past the obstacle. And what I love using to sharpen that logic and math muscle is Brilliant. Brilliant helps you excel in math and coding with step-by-step interactive lessons and personalized practice. Learn by doing. What I like about Brilliant is you're not just putting a playlist on autoplay and then scrolling on your phone. You're actually learning by solving problems. And the courses are made by world-class teachers from MIT, Harvard, and Stanford, designed for anyone from the ages of 10 to 110. I especially love the courses on coordinate geometry and algorithmic thinking because they cover exactly the kind of stuff I'm talking about, sharpening your logical thinking skills. To learn for free on Brilliant for a full 30 days, go to brilliant.org/Tariq10x, scan the QR code on screen, or click the link in the description. Brilliant's also giving my viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. Alright, now we can go deeper without getting lost in the sauce of spicy syntax. This sounded weird, right? Okay, let's first take a look at the build toolchain. I want to show you something very interesting. Now, if we take a look at the make file, we will see this. So basically, without getting too deep into this, this compiles, this links, this binds for DOS4GW, compile OK, link OK, but what the hell is a DOS4GW? So early DOS machines had a 1 megabyte address space, and IBM's PC memory map reserved the top chunk of it, leaving only 640 kilobyte as normal program space. That wasn't a random evil limit, it matched what early 80s software and hardware needed. The problem is, games like Command & Conquer were much bigger, so this old model became a problem. DOS4GW is the extender layer that moves execution into a larger protected mode runtime. So the game isn't trapped in the 640 kilobyte DOS box. Okay? DOS4GW is the runtime layer between the game and all DOS services. Think of it like as an adapter. So eventually the runtime looks like this. Game executable on top, then DOS4GW, then DOS services, and then hardware. This setup gave the game executable much more runtime headroom than plain default DOS. Now, another interesting thing is, if you take a look at some headers, compiler assumptions are baked right into source. As you can see, we have hard coupling here. Build toolchain, runtime layer, and compiler-specific header behavior are all connected. The cost of this is portability depth when moving to modern compilers and platform targets. It makes porting the game much more time-consuming. Okay, next chapter. Let's talk about the game assets and engine code. As I mentioned at the beginning, games are usually built out of two parts, the engine and the assets. Of course, there are many other things, but you can put most of the things in one of these two categories. In many engines, that boundary is pretty hard decoupled. You can swap content data, adjust rules, and get meaningful gameplay changes without touching core engine code like ever. Think about games where it's pretty easy to add new weapons, enemies, maps, whatever. This is one of those moments where this engine clearly differs from more hard decoupled designs. At first glance, it looks clean. You got assets in the mix files and the engine written in C++, and boom, done. But During my code study while preparing this video, I stumbled upon many, let's call them interesting things. And let me cook for a moment. For example, if we follow one simple question, what makes a unit buildable? We will immediately hit tight coupling between content identity, the assets, and gameplay authority, the engine code. That coupling is exactly what slows iteration later. If you open out the source code and go into the unit declarations, we will find this. So static infantry type class const E5. Now this is some infantry unit, and this struct tf prerequisite is gameplay authority, and it lives in compiled code, not a freely swappable external rules table. Then if you go in the next file, same story on units. For example, unit f tank. So right away, if the game designers want to change game rules regarding the build prerequisites, for example, you are touching C++ declarations. And this is the first coupling pressure point. But let's continue. And this is where the story tightens even more. The same declaration data also drives asset lookup keys. For example, in idata.cpp, let's go quickly over the syntax. Makepath builds a file name string. So if any name is, for example, flametank, this line builds flametank.shp. Then mixFile class, retrieve full name, asks the mix system, give me the pointer to this file's bytes. And then this void const uClass blah 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 image data means save that return pointer into this unit's image slot. This sprint buffer blah 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 uClass any name line builds the cameo key version like flame tank icon, and then the same retrieval flow runs again for sidebar image data. All of this is not so important. You don't need to understand this whole syntax. My point is, now for one concrete unit, the flame tank, the same source record is controlling both gameplay fields and which asset keys get requested. And that is the coupling core. One C++ unit definition is doing double duty as a rule definition and content key definition. And then if we go to the next file, for example, house.cpp and scroll, and we will see even more coupling is added in the runtime legality. Now, this is interesting because here the game decides if the button is legal this frame. And it is reading source-defined fields like pre, level, and ownable. And those fields are part of shared engine schema. So from top to bottom, this path is tightly coupled. The declarations define rules, the same declarations feed asset key lookup, and runtime legality checks consume those same fields. Now, why you shouldn't do this? Because now a small content tweak can become a code change, a rebuild, a multi-file validation pass, and you also lose clean ownership boundaries because content edits and engine rule edits are entangled. Now, compare that to harder decoupled pipelines where gameplay rules live in external data schemas and the engine mostly interprets just and validates. In that model, changing a build prerequisite is just a game data change. You shouldn't need to change engine code in order to change some game rule that defines if a specific infantry unit can be built or not. And that is the practical difference. Decoupled pipelines optimize iteration speed. What can we learn from all of this? As you know, I always talk about trade-offs. And you have to realize there are good trade-offs and not so good trade-offs. The real lesson is to pick your trade-offs properly. If your priority is strict deterministic behavior under tight constraints, this approach can work. Obviously, I mean, the game was a huge success. But if your priority is fast content iteration and safer ownership boundaries, hard decoupling between asset data and gameplay rules just scales better. And now my 2 cents to all of this, I would generally not advise doing it this way in 2026. let's proceed with the next chapter. Now let's open Function.h, because this file tells you a lot about the architecture style immediately. Function.h is included by almost everything and includes almost everything somehow. It's like the center of a spider web, but let's walk through it, okay? At the top, it already mixes platform and compiler setup. Then right after that, we get a huge include wall. It includes basically everything since the dinosaurs. So one file is pulling in a massive part of the engine surface, and it keeps mixing concerns in the same place. So yeah, this is a true tarantula pattern, Exodia, whatever. One global header included almost everywhere, carrying platform config plus networking plus QAPI plus gameplay facing declarations. And for the record, in this project, Function.h is included by around 150 out of 156 CPP files. So if you touch this file, you touch almost the whole build. The problem with this is it creates this huge blast radius when you want to rebuild it, because it's basically everywhere. And one quick historical note. This was not done during some no version control era. The source has header metadata with VCS paths, for example here. So the issue is not they had no source control. I mean, I don't know to which extent did they use source control, but they didn't have Git or other modern development tools, that's for sure. Now, the issue with this approach is coupling. This header became the global dependency hub, which is expensive to maintain and refactor later. Nowadays, this is for sure something you should not do, or let's put it this way. It would need to be an extremely special edge case where something like this would be justifiable. Another problem is the lines between modules start blurring so much that basically everything becomes everything. A monolith of death. Okay, let's continue with the next chapter. This chapter is probably the most complicated one, and I gave my best to simplify it as much as possible. Let's talk about the event queue, netcode, lockstep, etc. As we already framed in the whitebox chapter, player input and network traffic converge into one event pump. In this chapter, we're gonna zoom in and follow the exact flow. Now, to give you the right mental model for this chapter, let's break it down into steps. First, we're gonna pick queue branch by game mode. Then we're gonna trace the single player baseline. Then we're gonna add multiplayer on top, so build a packet header. Then we're gonna dispatch the packet to the right path. So let's start with the mode switch. Okay, first we need to pick up the correct branch depending on the mode we are playing. If you are in a single player, the switch case goes to QAI normal. If you are a multiplayer, switch case goes to QAI multiplayer. Okay, next step, how does the event flow from out list to do list work in single player? So this is our single player baseline. In single player, local commands are moved from out list into do list, then executed if frame ready, then cleaned. Important detail, since this is the single player path, there is no packet header build step, no build send packet, okay? So this is our baseline. Now on top of that, we add the networking layer. So in multiplayer, we still use the same out list and do list, but now we must package events before sending them. So first we build the packet header. Now we have the header container. And next step is dispatching to the correct event packer. Now in Command & Conquer Tiberian Dawn, we have the compressed path and the uncompressed path. And in multiplayer, we use the compressed path. Okay, after dispatch, the compressed packer does the core move. Take event from out list, stamp it, add to local do list, and write to packet. And this is the lockstep moment. One local click now has two jobs. First, queue for local future execution and send out to other players. This chapter is the low-level view of the same white box story. And I tried to really simplify it. I left a lot of low-level details out of this explanation because I tried just to map out the most important parts of the event queue system. But basically, if you want to remember one thing about this is we have two inflow lanes which converge into one execution queue, which is frame scheduled, and we use CRC just to check the sync policing. The trade-off is the classic lockstep trade-off. You give up flexibility and add queue timing complexity, but you gain deterministic replayable behavior across peers. In case you didn't know this, early FPS games like Doom 1 had also lockstep multiplayer. Okay, let's continue with the next chapter, Fog of War. Fog of War in RTS games means this. You only see what your units can reveal. In some games it's like once the field is revealed, it stays revealed, in some it turns back to black. In this Command and Conquer flow, once a cell is mapped, this path does not turn it back to black. Back to black. Now, one of the most important things to understand in this Fog of War implementation is units do not all share one fixed vision number. Each type has its own sight range. So one type can reveal more cells than another. And in this implementation, the key trick is this. The map is handled like a one-dimensional cell array, and Fog Reveal uses two pre-computed tables to avoid heavy math every update. At first, this looks wild, but once you see it, it makes perfect sense. So this array, radius offset, is a collection of direction commands for different sight ranges. If a unit has sight 0, then offset directions is only this value. If it's 1, then we have these values. These values literally describe directions from a center point. So imagine we are in the center. This is, for example, left, up, right, down, up and left, down and right, etc. The other array, radius count, describes how many values are to be used for each sight range. So for 0, we have only one value, and that's indicated in this element. Simple, when you know what it's about. So radius offset stores those relative jumps, and radius count tells how many jumps belong to each radius. So when a unit stands on some cell, the engine just walks these pre-computed jumps and checks which cells should reveal. Important part, the table itself does not change per unit. What changes is sight range, and that value decides how much of the table gets used. That is why this works as a fast lookup. Same table, different slice size depending on unit type. Now one concrete example. We have one infantry unit on the map, it moves a bit, and the game runs sight update from that unit position. Here's what those lines are doing. Sight equals class sight range pulls the reveal radius from this infantry type. Coordinate cell converts world coordinate to map cell index. Map sight from starts the reveal routine with center cell, radius, and incremental or full mode. Now inside sight from, first it checks if this reveal pass is even valid. So we have this and this. So in plain terms, in radar cell means center cell is outside valid map radar bounds, so exit. And sight range greater than 10 means invalid radius, so exit. No valid input, no reveal pass. If valid, this is where those two tables are used. This block sets up the scan. This picks how many jumps to read for this unit's radius. This points at the start of that jump table. So if one unit has smaller sight range, it reads fewer offsets. If another has bigger sight range, it reads more. If incremental is true, it skips inner offsets and keeps only the outer ring delta. That is the optimization part while units keep moving. Then each candidate cell is tested and only valid cells are considered. Then this per cell filter kicks in. This applies one job from the offset table to the center cell. This drops out of map cells, and this checks horizontal wrap overflow safety. Then we have this drops cells outside real radius. So yes, this is the exact is this cell inside the sight area gate. If yes, and if the cell was not mapped yet, then reveal flip happens. Okay, as I said in this command and conquer, once the cell is flipped, it stays flipped. And this part is the flip gate. This means reveal only runs once per cell in this path. This is the handoff that performs the actual map state change. And inside that function, as I said, if already mapped, return immediately. Else set is mapped equals true, set is visible true, and request a redraw. This is where the cell is effectively flipped on screen state. So for radar, it's the same truth source. Radar asks display class map cell first. Only if that reveal call returns true, only then it redraws the radar pixel. So map reveal is the shared truth source. Radar is just a consumer. So from one infantry move, the chain is this: unit coordinate, center cell, radius scan, valid cells, map cell, flip state, radar mirrors it. The lesson from this implementation is this: we have only one source of truth for the cell visibility, but we can have many consumers, many displays, calculated once and then pass it to each rendering consumer, which in our case is A, the map that we see, the gameplay that we see, and B, the radar, which is in the right top of the screen. Okay, last chapter, pathfinding. Pathfinding in RTS is the part that turns your click into movement. If this breaks, the gameplay looks bad immediately. Step 1. The click does not move the tank directly. It creates a move intent. So action move handles the click. The pixel to coordinate line converts mouse pixels into world coordinates. Then this line creates the real move intent. The voice lines are just audio feedback. As you know, when you click on a unit and want to move it, it gives you audio feedback. The important line here is this queue mission. The move command is queued and later executed by gameplay runtime. So far we only have the intent. When runtime picks up that mission, it resets old path state and prepares a fresh route. If you played any RTS game, you know that if you want to move a unit in a different direction that's already moving, it will only take the last movement command and ignore the previous one. Assign destination updates navigation target, path facing none invalidates current step list, and start of move starts movement processing if the unit was idle. With all path invalidated, the planning can start. This is the key mental model. The solver returns a direction command list, not a giant per pixel trajectory, okay? So we have this path type struct. Length means how many movement commands. Command points to those direction steps. So the path is basically how many steps to switch directions. Okay, so now if you open this find path CPP file, you will see it starts empty and then we start adding steps. From here, the solver tries the simplest move first. Go straight forward to the destination. If that fails, this is where the hybrid part really starts. The algorithm then tries edge follow on both sides of the blocker. Then it picks the shorter candidate by comparing the lengths. So the unit is not guessing blind. It tries both detours and chooses the cheaper one. Once the solver is done, those commands are copied into the unit runtime buffer. From this moment, movement no longer asks, where should I go every frame? It just consumes these prepared steps. And now we shift from the planning phase to the execution phase. So basically pathfinding works like this. One click becomes a queued move intent, the route has been built, then we get the command list, we start consuming it step by step, and then if blocked, we replan the movement. And this is the hybrid approach here. First try directly going forward to the destination. If that doesn't work, then start recalculating your path. Simple and deterministic. Conclusion. Good enough beats perfect. You don't need perfect code to create great products. And I already see someone typing, so you're saying memory leaks are good. No, I'm saying you have to be pragmatic and maybe start listening what people are actually saying. The Command and Conquer devs were not clueless. They knew exactly where the code was ugly, where the coupling was nasty, and where the header file is basically a war crime. But they also understood at the end of the day, the only thing that matters is the player experience. The tank still moves, the fog reveals, multiplayer stays in sync, and the game feels right. And here's the part that people don't like admitting. A developer's skill shows up in where they spend their time, which parts they polish until they are rock solid, and which parts they look at and go, this is good enough. Why? Because time is a constraint. Always. Now you can say if someone does something suboptimal on purpose, they're obviously bad. Sure, if time wasn't real, if deadlines didn't exist, if opportunity cost didn't exist. But software engineering isn't some esoteric discipline where the goal is to create the most elegant solution in a vacuum. The goal is to build a product in a good time frame while the world keeps moving. You can over-engineer the best cassette player ever made, but if it takes you 20 years and production starts after cassettes are obsolete because CDs took over, what's the whole point of it? And that's why great developers don't just write code, they manage trade-offs. They choose constraints, make them explicit, and invest effort where it actually affects the product. They don't overthink details nobody cares about, and they don't under-engineer the parts that make the whole thing collapse. And that's why Command and Conquer Tiberian Dawn is a masterclass in that aspect. I mean, they shipped a legendary product with great timing while consciously compromising parts of the code base that the end user will never see, never understand, and never really care about. So the lesson is very simple. Do not over-engineer the parts that don't matter, and don't under-engineer the parts that make your product not suck. Ship the game, learn, do it cleaner next time. And Command & Conquer is the proof. The code has its flaws, but the product was legendary. Now I want to take the moment and say a big thank you to my Patreons and YouTube members. If you want to support the channel, you can become a Patreon or YouTube member. I will be releasing bonus content for members and Patreons. I mean, these guys have really been supporting me for a very long time without getting any extra perks. And I think it's time to start giving you some extra material on a regular basis. So that's it for today. If you like the content, hit like and subscribe, and see you in the next one. Tariq 10x.